Hey everyone, welcome back. We are learning about semiconductors. In the previous video, we saw what is a conductor, semiconductor, and an insulator, and we also took a quick peek on how semiconductors looked like in ancient days. In this video, I'm going to walk you through the types of semiconductors. Before getting into the types, we'll also see how semiconductor materials exist in nature. They occur as simple elements and as compounds. The most common are silicon and germanium, out of which silicon is the most preferred semiconductor material. One common reason is that silicon is sand, which is abundantly available in Earth, so it's very cheap. The other reason is that the peak inverse voltage of silicon is very high, and the band gap of silicon is 0.7 electron volts, whereas the band gap of germanium is just 0.2 electron volts. So even a little amount of excess heat could destroy a germanium crystal, whereas silicon is not that easily destroyed by excess of heat. So the compound semiconductor material could be formed by combining different elements together. Combination of group 3 and group 5 elements gives you some semiconductor materials like gallium arsenide and gallium nitride. Combination of group 2 and group 6 elements gives some semiconductor materials like zinc selenide, zinc sulfide, and combination of group 4 elements with group 4 elements themselves gives rise to some semiconductor compounds like silicon carbide, silicon germanium, and lots more. So moving on to the different types of semiconductors. We have intrinsic and extrinsic semiconductors. Intrinsic semiconductors are also called as the pure semiconductors. This is because one semiconducting material atom combines with a similar semiconducting material atom. Take a look at this example. A silicon combines with other silicon atoms to become stable and conduct electricity. The atomic number of silicon is 14. So, the valence shell of silicon has 4 electrons. Now this atom requires 4 more electrons and a total of 8 electrons to become stable. So this silicon atom combines with 4 other silicon atoms and conducts electricity. However, the conduction is a little less than that of extrinsic semiconductors. Let's see why does this happen. So extrinsic semiconductors is the next type of semiconductor material. This is also called as the impure semiconductor. This is where there's a new concept called as doping. Doping is a process of adding impurity to a pure semiconductor. Depending upon the type of impurity that we add, the extrinsic semiconductor is also classified into 2 types, a p-type semiconductor and an n-type semiconductor. When we add a trivalent impurity to a pure semiconductor, it forms a p-type semiconductor. When we add a pentavalent impurity to a semiconductor, pure semiconductor, they form n-type semiconductors. So what do these trivalent and pentavalent atom mean? A trivalent atom means the atom has 3 electrons in its valence shell. So here are some examples like boron, gallium, indium, and aluminium. All group 3 elements of the periodic table have 3 electrons in their valence shell, forming a p-type semiconductor. Now a pentavalent atom means the atom has 5 electrons in its valence shell, like phosphorus, arsenic, and antimony. When you add these pentavalent atom impurity to a pure semiconductor, they form n-type semiconductor. So first let's look at p-type semiconductor materials. So as we saw, a p-type semiconductor is obtained by adding a trivalent atom impurity to a pure semiconductor. Let's consider the example. Boron is added to a pure semiconductor. Now since it has only 3 electrons in its valence shell, there's lack of 1 electron here. Now due to lack of 1 electron, it gives rise to an energy state called as a hole. Now this hole is capable of moving in and around the atom everywhere. So when the hole moves, the electrons tend to occupy this hole. Now this area is filled, however there is this empty space that is left behind, so the hole moves here, and the hole carries a positive charge of plus Q. And this is how the hole moves in and around the atom, and so the conduction of a p-type semiconductor is due to holes. Now let's take a look at the energy band diagram of p-type semiconductor. There are more holes in the valence band. And these atoms are called as the acceptors because they lack free electrons and so they're ready to accept free electrons from others. So the conductivity that is caused by a p-type semiconductor is called as p-type conductivity. Now when I apply a potential difference across a p-type semiconductor, all the holes move towards negative charge. As we know, opposite charges attract each other. So the majority carriers here are holes and the minority carriers here are electrons. Usually people get confused that in a p-type semiconductors there's only holes because P stands for positive and holes are positive. However, there are electron carriers too that contributes to current in a p-type semiconductor. But the concentration is very minimal and the concentration of holes is very high. And you also have the electron hole pair generation in a p-type semiconductor. Now moving on to an n-type semiconductor. As we saw, an n-type semiconductor is obtained by adding a pentavalent impurity atom to a pure semiconductor. Consider this example. We are adding in antimony to a pure semiconductor. Although atomic number is 51, the valence shell of antimony has 5 electrons. Now, we know that only 4 electrons is required to make this lattice structure stable. But antimony has 5 electrons, so there is 1 free electron that left behind. And this free electron also has the capability to move in and around the atom, contributing to the flow of electricity. Now let's take a look at the energy band diagram of an n-type semiconductor. There are more free electrons and very less holes in the valence band. And these atoms are called as donors because they have free electrons in excess and they're very good that they want to donate everything that they have in excess. And the conduction caused by an n-type semiconductor is called as n-type conductivity. Now when I apply a potential difference across the n-type semiconductor, the electrons move towards a positive charge. So the majority carriers here are electrons and the minority carriers here are holes. And you also have an electron hole pair generation even in n-type semiconductors. Now, apart from the above difference of a p-type, n-type and intrinsic semiconductor, let's also look at some more differences. Now, the conduction of an intrinsic semiconductor depends only on the number of charge carriers, but in an extrinsic semiconductor, the conduction depends upon the amount of impurity that we add. Like even in n-type semiconductor, the conductivity is actually very high than that of a p-type semiconductor. And also, I can state that at equilibrium, for an intrinsic semiconductor, the hole concentration and the electron concentration is almost equal because I'm not adding in or taking out anything from the atom. But in an extrinsic semiconductor, that's not the case. The electron concentration is more for an n-type semiconductor and the hole concentration is more for a p-type semiconductor. There's one more concept called as the Fermi level or the Fermi energy. This is the thermodynamic work that is required to add an extra electron to the body. The Fermi level is at the center of the conduction and valence band for an intrinsic semiconductor. But for an extrinsic semiconductor, the Fermi level varies with a p-type and n-type. For an n-type semiconductor, the Fermi level is just below the conduction band, and for a p-type, the Fermi level is just above the valence band. So we've come to the end of this video. So long story short, in this video we saw elemental and compound semiconductors. We also saw the types of semiconductors, an intrinsic and extrinsic semiconductor. And an extrinsic semiconductor, it's again classified into 2 types, p-type and n-type, which is based on the impurity atom that we add to pure semiconductors. In the next video, I will walk you through the different semiconductor devices that exist today. Well, thank you for watching and stay tuned for more videos.